And the boundary of D is piecewise smooth. A reasonable boundary equipped with the induced, this is what we call standard orientation. Now, in this case, it's not so difficult to understand what that means. So, for example, we have a smooth boundary, D. Then we draw a picture of the normal vector pointing outwards. Outwards pointing normal vector. And then we make sure that the orientation of the boundary is such that the two vectors are normal and then followed by the tangent vector should be positive. And then in Mickey Mouse mathematics, I actually can tell my grandson this, you can run around the boundary, which he would like to do, run around the boundary, and the domain is on your left. So the domain is either on your right or your left, and the induced orientation means it. So run around the boundary. And B is on your left. For higher dimensions, when the boundary is not just a curve or a piecewise curve, union of piecewise curve, it's more difficult to say, and I explain to you what you do. It's the same idea as this. Okay, the boundary is oriented. So this means that there's an integral. So if omega is a one form, and it's over the reals, for example, f dx plus g dy over the reals, or it's very convenient to write over the complexes, let's say, I don't know, let's make it interesting, f dz plus g dz bar over the complexes. These functions being complex value. So if you have a one form, which you write either over the reals like that, and we talked about what it means, or you write it over the complexes if it is a complex value one form. This thing is defined. And there's a special case, which is important. It's important when the one form is omega is d of a function. So it's more or less related to what is related to the gradient in this case, which is this, which we wrote down. That's a special case. And the fundamental theorem of calculus is simply that the integral of dh of a function over a curve, so in particular over one of these curves on the boundary, is equal to h of a function at the end points evaluate. That's the fundamental theorem of calculus. Sometimes I write H evaluated on the two endpoints. So you know that, and the proof is the same. There's nothing more to do. And we regard this as the integral over the boundary of the curve of H. Well, the curve is only boundary of the curve is only points, but that's the way we think of the integral over the boundary. And then for omega as above, so let's write it over the reals, dx over the reals, dy. Then, I don't know the history of this, but we introduce the boundary of the form. It's an ancient thing to do. It is the partial of g with respect to x minus the partial of f with respect to y. And you have to really think of this as a two-form, which is alternating because of area. Alternating, the physicists would say here, area form, due to orientation. And that's the reason it's minus signs here also. And the thing to note here is always that d omega equals 0 really means that the partial of, well, I'll write it down, with respect to x equals the partial of f with respect to y. And this is the necessary condition. I talked about this last time for omega equal dh. Because if it's dh, you will have this, and that necessarily, if this is then f and this is then g, and the partial of g with respect to x has to be the partial of f with respect to y if it's really going to be of this form. This is necessary. It's a necessary condition. Necessary condition. And now you should be big boys and girls, and you should write A. I'm following the notation of standard notation, for example, of Grievous and Harris. So A is the C infinity functions. And when I write A, I mean complex values, because that's all we're going to do here. Real value is just a special case. And A1, the C infinity 1 forms. And A2 equal the C infinity 2 forms. And I will write here C to be the constant functions. Those are the three things that we have so far discussed. Well, the constants I play a role, of course, and then C infinity functions, and then C infinity 1 forms, and C infinity 2 forms. And you should think, if you take a function and you take d of it, you get a 1 form. And if you have a 1 form, you take d of it and you get a 2 form. And if you look at what happens if at this level d of a function is identically 0, so that identically 0, what happens here, if d of a function, then the function is a constant, f is locally constant at least, because it means the gradient of this function is 0. So here are the constant functions. Please keep this in mind. It's a way of summarizing things. If you take a constant function and regard it as a C infinity function, d of it is 0. If you take d of a function and regard it as a 1 form here, d of it is 0. If you take a 2 form, d of it is 0. That's just a way of organizing this data that is here. Okay? When you're big boys and girls in mathematics, you will call this the round complex. And this is very much related to understanding this thing is very much related to the geometry of the domain. So just keep in mind, this is as the Germans say, Zukunftsmusik. This is the music of the future, but it is very fundamental music of the future. The Durand complex is more or less telling us the geometry of D. And that's God calling on your phone to agree with me. Okay, so when you go home at night, say the Durand complex really says something about the geometry of D. We will see this throughout the course. I don't want to formalize this now. This is, however, a fundamental first step in understanding geometry by analysis. Geometry by analysis. This is analysis, and this is geometry. In particular, this is complex analysis, and all of this, the first person who understood all of this is Riemann. So Riemann understood this. And Riemann is the great giant. We are standing on the shoulders of Riemann. Okay, that's just a little bit of Zukunftsmusik, future music, about why this is important. So, the main reason in dimension 2 why this is important is Green's theorem. I indicated a lot about this last time. Green certainly did not prove this in a mathematical sense, and I think no one proved this in any sense until Riemann proved it in the mid-19th century. And in fact, I'm not sure there was any good proof until Bourbaki after the Second World War. So Green's theorem says that, and I'll write it from the point of view of this. We call that a Durand complex. I'll write it from the point of view of the Durand complex. The integral around the boundary of the domain of omega of a 1 form is the integral. I don't need to write it. This is one-dimensional, so that has to be a 1 form. It is integral over the domain of d to the 1 form. So it's not very hard to remember this. The integral over a boundary is the boundary of the form over the domain. So this is capitalism. You pay your price for getting rid of the boundary by taking the d of the form. It's a very small price. Okay. So let's do this. That says in coordinates. So over the real numbers, So the integral around the boundary of f dx g dy is the integral over the domain of partial of g with respect to x minus partial of y of f with respect to y dx wedge dy. I emphasize orientation here, but that's really the area form. Engineers and physicists might write this as dA. And some of these people might call this thing a line integral. I never do, of course, but you might see it called a line integral. And those people who call it a line integral quite often put a little circle around here. I don't know why, but okay. But the statement of the theorem is this. And this theorem is much more than a theorem, it is a deep philosophy. First of all, the theorem is true in complete generality. Second of all, the theorem is really something philosophical. What does it mean boundary? What does it mean boundary? It is a very, very deep theorem. Now, in the modern mathematical literature, this is called Stokes' theorem usually. Stokes' theorem. Well, Stokes was interested in three-dimensional geometry and three-dimensional fluids and things of this type. So he sort of proved this in dimension 3. Again, 19th century type mathematics. Again, all of these things were proved by puzzling the domain in some sense. Okay. So let's write this over the complex numbers. The integral over the complex numbers, I'll write the same thing. Now let's see if I can copy the notation. Where the heck is it? Oh, I made big letters for the complex one. Okay, I don't care. So f dz plus g dz bar. Now these things are complex values. And that's what we're going to use. Well, it's the same thing. It's the integral over the boundary. It's just writing down what the boundary operator is. It's partial g with respect to z minus partial f with respect to z bar dz wedge dz bar. The point is that over the complex numbers, this frame, what we call a frame, this thing over C, what this spans over C, what you get when you take linear combinations of dz and dz bar, is the same thing as when you take linear combinations with dx and dy over C. Right? So there's nothing fancy about this. This is just writing things over C instead of over Y. Okay? Okay. So that is the theorem. And now let us write down a corollary. And you begin to see how deep this is. Corollary. Integral of, maybe now over the boundary of D, of, let me write here, H, dz, where H is holomorphic, is, now let's just use the philosophy, that's integral over D of now let's see here, what do I have to do? I have to take the coefficient of the z bar thing and integrate it with respect to z, but that's nothing, so that's 0. Minus, and then the coefficient of this thing with respect to z bar, dz bar. Well, let's be a little bit more convincing with the dz bar is a good guy. Let's write it down. You see, these are the kind of things you need to do for yourself. I get tired of doing them. I've done them hundreds of times in my life, and I'm really fed up. So anyway, you have to do it yourself. And now dx wedge dx is 0 because it's alternating. Dy wedge dy is 0 because it's alternating, so you only get dx dy, and with a minus sign, and minus I is 1 over I, so you put that downstairs, and now I think I get the same, yes, we have the same thing here, and so we got this, and this 2 over I appears every place in geometry because, you see, this thing really is not real. So it's 2 over I times dx dy. So quite often we scale to make this thing real, to make it real. And so the key, so the area form here then becomes, you scale it, all right, I over 2 d z, what, dz bar. Okay. So that's the area form, written in complex form. And now, so this is this area, this is more or less area, I just had to scale it. And now what happens if this thing is holomorphic, this thing is the Cauchy-Riemann equation. So if you take the partial derivative with respect to c bar, it is equal to 0 because of holomorphicity. This is the Cauchy-Riemann equation. So you can start this lecture, if somebody understands Stokes' theorem and believes everything in life, by saying, well, you have Stokes' theorem and holomorphicity means d bar is 0, and therefore we have the corollary, the integral over the boundary of d of h dz equals 0 for h holomorphic. That's power. That's an incredible theory. Okay? This even has a name. This is called the Cauchy integral theorem. Now, Cauchy didn't prove it completely. And I said Riemann proved it. In fact, maybe he did, but if he did, he assumed something. Okay? So in order to prove this, you need Stokes' theorem. Well, okay, Green's theorem, it's the same. Stokes' theorem in dimension 2 is Green's theorem. And this requires H to be C1. Continuously differentiable. Every place you see here, you differentiate at H. Right? So for example, someplace up there, there it is. There's the derivative of H. Now it's 0 maybe, but I mean, in order to discuss this whole thing, Stokes' theorem and so on, it has to be a continuous function. So you really need H to be C1 for Green's theorem. Okay. That's really what you need. Many mathematicians have tried to understand this, why we need this regularity. Of course I was lying in the sun in the mountains thinking about this. It's the kind of thing you think about when you're old and lying in the sun in the mountains. It's very nice. But I really don't understand the proof I'm about to give you. Of course I understand it, but I don't understand the philosophy, why we need this proof. So if you have some deep idea about why we need the proof I'm about to show you, I would be happy to discuss the matter. So, Goursat's regularity theorem. learned something a great deal. There's some physicists here, and I learned a great deal from physicists. I have to tell you this. Physicists don't worry at first about the detailed conditions you need to prove something. I don't mean that negatively, I mean that absolutely positively. My physicist friends whom I work with tell me, and of course they understand physics, I don't, physics is too difficult to worry about that. The real world is far too difficult to worry about some technical formal, they call it formal, and I hate it when they call it formal, to worry about some formal mathematical condition, right? We're going to start. I mean, try to understand the real world. We're going to start and see what we can prove. In mathematics, it's like Latin. With analysis 1, 2, 3, and so on, and so on, and so on, right? It's just like Latin. Everything, you have formal structure. You learn all this stuff. Maybe it's also even a little bit like computer science because it has to be formally correct. But physics does not have to be formally correct in any sense. There are many things in physics, for example, where my colleague and I admire him greatly, Huckleberry said to me, that is a theorem which can never be proved. So this theorem he's talking about is proved with Feynman diagrams, and Feynman diagrams are not a proof. It's something else. It's understanding nature. So these people in the 19th century, such as Riemann in particular, was almost a physicist, that didn't worry too much about what was being assumed here. So the fact that this was only proved later, much later in the 19th century, is not surprising. And the fact that you don't know about this guy is not, you've never heard his name. And he's not a famous guy. Yeah? And but he wanted to make sure this theorem is on a sound basis. And so he made a nice contribution. But the real contribution here is made by almost physical thinking. Green, Cauchy, Riemann, thinking what is really true here. Let's worry a little bit later about what are the assumptions. So the Gauss's regularity is if H is homomorphic in a neighborhood of a point, then it is C1 in that neighborhood. It is even. Yeah, it is at least, well, it is C1 in that neighborhood. In fact, this regularity theorem, in fact, say if the point at H is equal to a convergent power series about that point. Let me say this. Convergent there it is, convergent about that point. We'll talk about neighborhood of a point, let's say C is 0. That's very interesting. In the middle of Gauss's proof, at the end of Gauss's proof, he proves this, and of course that is more than C1. This is what we call an analytic function. This thing is much better than C1. He uses result of Cauchy in this context, and this is called the Cauchy integral formula. So you see, so even though Cauchy didn't worry about too much the assumptions in the middle of all this even Guazzard needs his formula, and I abbreviate this throughout complex, I call it CIA. So the goal of today's lecture, I have time I think, is to prove the regularity theorem and prove Cauchy integral formula, and to say then that holomorphic functions are just power series. Yeah. And you can argue, perhaps correctly, that you can just start the lecture with the definition of holomorphic as a power series. Okay, but I think it's interesting to see the way things developed. Okay. And Guazzard had this idea, and I'll call it, to make you think of it every time, I'll call it Guazzard's rectangle. All right. Okay, so the first thing is, you shouldn't fool around integrating over horribly complicated curves. You should fool around integrating over the simplest thing you know, which is a rectangle or a square, but let's say a rectangle. Okay. And there, of course, you know Stokes' theorem, that's easy to prove. So, for smooth. So here's a rectangle R. Let's draw it this way. And I'm in the plane, so I'm going to indicate the orientation as we know. You're running around the boundary with the rectangle on your left. Okay. And we have this thing, which is H holomorphic in the neighborhood of R. That's our assumption. So assume H holomorphic in the neighborhood of R. So in particular, continuous. Okay, holomorphic is continuous, we know that. And Guazzard's theorem is Guazzard proof. So let me call this Guazzard 1. Prove two things. The integral around the boundary of R of H dz is 0. So his idea was to prove the Cauchy integral theorem for one specific boundary and use that fact. Okay. So you see H is continuous, so there's no problem with this integral. The problem happens when you take d of H, because you don't know anything, right? So H is continuous, so there's nothing wrong with that. So let me give proof of Guazzard 1. It's amazingly simple. And it's based on 19th century logic. Guazzard says, well, guys, Riemann's been doing this for years. Let's just partition this thing up into subrectangles. Right? And the integral around this boundary is the integral around this thing. I see this in, for example, Maxwell's argument. I mean, physicists always think about this. So, and now the integral, well, let's make a color so you know what I'm talking about. So let's say the white integral over here, this is R1, this is R2, this is R3, R4, 4 rectangles. And if we're integrating around R2, say it looks like this, it looks like this, it looks like this, and you see, of course, this cancels with that. Right? And the same thing, the same thing, for example, up here, the integral around this guy is here, 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 here. So this cancels with that, and so they all cancel. So that's almost stupid. It's the integral around r, I'm not going to write it all down, is the sum of the integrals, is integral around r1 plus and so on, r4. Okay. Well, then you make a very rough estimate. This is just amazing that this estimate works. This is an estimate that can be made by somebody who's not thinking very well. You see, you don't have to think to make this estimate. How many integrals do we have here? We have 4, right? So this is bigger than or equal to 4 times the integral in absolute value around, oh no, less than or equal to the integral 4 times the absolute value of the integral around, let's call this R max. Right? Because you have 4 integrals, and you find out the boundary integral that's the biggest in absolute value, and it's certainly estimated by that. Right? You can go home and tell your mother this proof is so easy. It's amazing that and then Guissat says, well, do it again. You're always happy to do it again. So if this is R max, then you do it again. And then maybe this is R max, and then you do it again. And if this is R max, you do it again and again and again and again. You're having fun. And then since you're a mathematician, you write down the answer. Right? So this all, you do it n times. So do it n times. And you get a nested sequence of rectangles. Rn. Now this n is different from that n. Maybe I'll make it different. Let's put it up above. Rn. Nested sequence of rectangles Rn. And so that the integral around the boundary of R of h dz is less than or equal to n squared times the integral around a boundary of Rn of h z dz. I think you're looking disgusted as me.
What happened to the 4?
Huh?
What happened to the 4? The 4 keeps getting multiplied.
That's n squared. Oh.
4 to the power.
Oh,
Yeah, it's 4 to the n.
4 is n. Well, let's see. Let's count to make sure. You're worried about counting here. What is it? How many do we have? The first time I divide, well, oh, I see. The first, I don't worry, some constant. So
There's some constant to the
yeah, there's some constant. I agree with you.
to the power of n.
So you agree. The first time we get divided. The first time was really the second time. That's n equal to 2. So we get 2 squared, right? And then we do it again, and we get 4 squared.
Yeah.
Oh, we're getting,
4 to the n.
4 to the n.
huh? 4 squared. Maybe I don't want to do, this is very good. I'm very bad at, we're getting 4 squared. I don't want to do it like that. I do it, I would like to, I don't want to do it's maybe delicate. I want to get n squared here. Is this going to happen?
No.
No.
When I divide it into 2,
I mean, can we always divide into n rectangles? But then we
no,
also get some again.
my idea was I divide the side into n and the base into n. Right? And I guess we get n squared rectangles or not, right? Isn't that true?
Ah, okay, so then that's how
We get n squared rectangles, right?
So you don't repeat the first process over and
What?
over. You don't repeat the first process over and over.
I can't hear you, I can't ever hear you. What?
So you don't repeat the first process for whatever, like for R marks and then the next R marks and then the next. You do it with smaller and smaller n's, right?
Yes, that's what I want to do. I would like to have n squared here, but what I started to do is dividing, I would have 2n squared, right?
which is also not bad.
Huh?
Which is also not bad because the perimeter is decreasing.
No, I don't mind putting a 2 here, but I'm worried about putting 2 inside the square. Oh, no, I don't care.
Yeah, it doesn't matter.
You agree? If I divide again with the way I want it, I get 2n squared. Because I'm just dividing these things in half. Right? And that makes the combinatorics a little bit easier for me. I mean, right? You don't mind.
Then n squared is also just fine. Just saying that it's
Yeah, it's order of magnitude n squared. That's, you know, I never think in exactly. I always think in order of magnitude. So 2n squared is okay. And that's what we do. We do n and 2n and so on. Okay, great. You scared me there for a minute. I thought maybe I didn't understand this. Okay. Okay. And that's really nice. This is Gurzat's idea. This is nested sequence. Oh, I put it in here up above. Right? This is a nested sequence. Everybody knows a nested sequence is, and they're getting smaller and smaller. So this nested sequence converges to some point z0. Okay. So now that's interesting because I apply the definition of holomorphic at S0. Apply definition of holomorphic at Z0. Okay. Let's recall the definition. F equals f of Z0 plus, well, it's affine, but let me even put the derivative as what it is. F prime is at Z0, whatever that number is. Z minus Z0, little o of Z minus Z0. Right? Now look at this guy here. It depends who your mother is. If your mother hasn't had any experience with mathematics, you might ask her just to integrate this affine part around the boundary. I mean, that's what you ask a calculus student to do in high school. But Gurzat is a little bit experienced. He says, I don't want to integrate that because I know Green's theorem is true for that. Because that thing is not only smooth, it's linear, basically. Right? So the integral of this thing around the boundary is 0. So I'm sorry, yeah, this is bad. So the integral here of this guy around the boundary of any of these things is 0, of Rn is 0. Right? Okay, so what we have is the integral hn boundary of n dz less than or equal to 2n squared, that's some trivial thing, put the square out here, times the integral of that thing, well that thing is 0, so it's the integral over Rn of little o of z minus z0 dz. Because the integral of the affine piece, the integral of the linear piece is 0. Right? And you're not surprised to know that this goes to 0. Check. Yeah, I mean,
So the way you are doing this is that you start with a rectangle and then you divide it into n squared pieces. You take the piece where the integral is the highest and then you bound it by that.
that's right.
That does not ensure that the rectangles where it reaches a maximum will be sort of nested. Because say when you say n equals 2, you get...
No, I just repeat the argument for the smaller rectangle.
In that case, the constant then blows up.
When a constant blows up.
So, because then you don't get the n squared factor. So what will happen is that, well, so you wrote down after the first iteration, right, it's less than 4 times the integral over the piece where it reaches the maximum.
Right.
Now, the integral around that piece is less than 4 times the one where, in the second iteration when you divide, right? So now you have 4 squared, and in the nth iteration you have 4 to the n less than...
Aha, so in fact you were right the first time, that this two is playing a role here.
Yeah, right, I mean, it's
4.
it's power to the n, it's 4 to the n, it's growing exponentially.
Is it really growing exponentially?
Yeah.
No, the whole integral is not, because, well, the integral is also, you're taking integrals over smaller and smaller regions. So somehow we'll have to use that, the perimeter is decreasing, because the perimeter is also decreasing at the same rate, and then we can use some argument like this.
Yes, but the small o doesn't decrease faster than exponential.
So, again, what Apik is saying, what everybody here is saying, is that this first estimate is not correct. The estimate I wrote on the blackboard here. That is not correct. He's saying this.
If you want your rectangles to be nested, then it's not correct.
Maybe they're not.
Okay, so in fact, that I see your point. You're right, but in hindsight, I don't need my rectangles to be nested.
But you do need the rectangles to be nested. How else do you
No,
know
because
that?
I need them to converge to something.
Then how do you know they convert to...
Right, I mean, because if you have a big rectangle here and a small one there, and then if they jump over all over the place, they...
Yeah, but I take a convergent subsequence. Of course.
You need the rectangles to be nested for there to be a...
No, I don't, I will not take them to be nested. I just take a convergent subsequence of rectangles.
There will be subsequence rectangle.
Huh?
But what if there's, for example, 2
No, what
convergent
is a rectangle?
subsequences that have 2 different limits?
There's so many people talking, I can't hear.
What we have is compact. The whole is compact with the whole.
Yeah,
original.
right.
I don't need nested.
You don't need nested then. Yes, so the...
I'm sorry, but it's a very good point, that you take a convergent subsequence of rectangles.
Yes.
Well, Maria doesn't like it still.
Yes, but if you have 2 convergent subsequences that go to 2 different points.
So what do I care? I have this estimate, I have this estimate every time.
Yes.
Okay.
Yes, you're right.
Yeah? So where did I write estimate? This is what's wrong. This is what's wrong. I take a convergent subsequence. To 0 to z0. I mean, as you're worrying, they're going all over the place, but I just take a convergent subsequence. Okay. And by the way, this number is important here, so that's why you scared me. Okay, thank you. Yeah, very good. So we have a convergent subsequence to z0, and now this is okay. Yeah? And then if you compute out what we have here, this is 1 over n times little o of n. It's incredibly fine. This is 1 over n. because the lengths of the boundaries of the rectangle are 1 over n. And so the boundary of the rectangle is 1 over n up to a constant, and then this little of 1 over n is the distance between z and z0 and so on. So thanks to your help of everybody, we have Gauss's theorem for rectangles. Okay, and that's the Cauchy integral field, yes.
Well, you have n squared, right? So you have n squared times that integral.
So you have n squared times that integral, the boundary term is 1 over n.
Yes, so that you
Is
get
1
rid
over
of
n, and the distance from z to z0 is
all of n, right?
is 1 over n, and so I get little o of 1 over n.
Of 1 over n, okay. Because
I mean, it's very tight, so anything, right? It's incredibly tight.
A little of 1 over n.
Huh?
Type O of 1 over n.
yes. Makes sense.
Yeah, well, altogether, this is this. Oh, this is 1 over n, thank you. That's what you did. Yeah. Okay, that's very, very good. Thank you, everybody. Okay. And now when you're having fun, you should do it again. And now you will see why I say this procedure of Gauss is in some sense a procedure which localizes the integral, and that is a technique that we all know about, so it's not surprising in some sense. So the same theorem, Gauss. So let's take Gauss's rectangle. So so the second thing is Gauss's punctured rectangle. More than punctured, but I'll write it that way. You know, you pay your money, take your choice. There are certain domains where this technique works. Here's Gauss's outside rectangle. And now let's take a point in the middle here. I don't know. I don't want to take Z0 because it was a point over here. Let's call this a point P. No, I don't want to call it a point P. I'll call it Z0 again. I don't Z0. And now I take a small rectangle around that. Oh, I made a mistake because that is the orientation. I want to take this as this boundary here as being the boundary, the oriented boundary of the other side. So I want to take it like that. Do you get what I'm talking about? Because I told you if you run around the boundary, you have to keep the domain on the left. So I want this to be the inside boundary. Okay. So let's emphasize that this is small. So let's call this thing inside here R epsilon. And let's call this big thing here R. Okay. so the boundary, the integral of same notation, holomorphic function, around the boundary of r minus r epsilon. So I pull out a small square, and of course I use the same technique. So the same technique, I just pulled out one of these squares, gives the same type of estimate. This is 0. Same estimates. Absolute same estimate, yeah.
But if you want to do the same procedure as before, you need a sequence of rectangles that converges to Z0, right? But then,
No. The method I used before, that's why I shouldn't have used this notation. Z0 is not the same Z0, so I'm sorry. Let me call this Z1.
oh, okay.
And the other Z0 where we had that other estimate is going to be here, some other place. All right? I'm just going to apply it to this. So anytime you can make something where you can make a puzzle like this, Goursat's method really works. The integral is 0. Okay? Okay. So what we learn is Goursat's puzzle works for certain domains. And now we have an idea that is pervasive in mathematics. It's called the method of singular integral operator. And this idea was already known to Cauchy. Here, Cauchy had already introduced something called the Cauchy kernel. The Cauchy kernel is this, k of z and zeta, function of two variables, equals 1, this is an amazing thing, 1 over z minus zeta, it's a one form, dz. Now let's suppose that we believe Stokes. We almost have something like Stokes here. So let's believe Stokes. Here's D. Let's say with smooth boundary. Here's the boundary of D. Here's a point which we're going to call zeta. The word singular has to do with the fact that 1 over z minus zeta blows up there. It blows up there, and you physics people should think of this as Dirac measure. What we're trying to, Dirac measure means you want something that blows up, that picks out the value. Do you understand what I'm saying? If you don't have any experience with physics, think about the following thing. This is metaphorical now, so think about the following thing. Here is zeta, yeah? And here is a Gaussian. right? And if you take a Gaussian like that, and this is a Gaussian, and this is a Gaussian with standard deviation epsilon. You take a Gaussian with standard deviation epsilon, and you take the limit as epsilon goes to 0 of the integral of a function against this Gaussian. So just to prove to you that I know what it is. Oh. I took the integral against the Gaussian. Everybody here has to take probability theory. So the integral against the Gaussian with mean value zeta and standard deviation epsilon. And I take the limit as epsilon goes to 0. You see, you're just picking up whatever happens at the point zeta, right? And you see what that is, that's f of zeta. So, so you see that's something like Dirac measure. The Dirac measure, Dirac introduced something called Dirac measure. It's the evaluation measure at a point. Right? A measure can do anything. One thing it can do is evaluate the function at the point. That's called Dirac measure. This thing is Dirac measure. This thing plays the role somehow of Dirac measure with the singularity there. You see, this thing is blowing up. In order to have integral 1 of Gaussian, it has to be like that, right? It has to blow up, right? It has to be Dirac measure. The same thing here. This thing blows up. Okay. Okay. So we apply Goursat's idea. Now I'm going to give you, Maria is now going to be happy. It's not Z0. This point in here is, I'm going to call it zeta. Okay. So I apply Goursat's idea. This is the big rectangle. And this is a point zeta, and this is a small rectangle, r epsilon. Now, in complex analysis, we prefer to scale this thing to make everything come out beautifully, so we put here 1 over 2 pi I. That's the correct scaling number. So the integral around the boundary of r minus r epsilon equals of h is holomorphic, hit it with a Cauchy kernel. So I write h of z to emphasize where we're integrating. Z, sometimes it's confusing where we're integrating. Z is in this boundary. Cauchy kernel, dz. Singular kernel. Okay. Well, the same method, you might complain, and it's my bad notation because Maria was worried about where z0 might be. This integral is 0. Yeah. And now, that says that the integral around the boundary of R of h of z, Cauchy kernel, the singular kernel, this is an operator. You see, the answer here is a function of zeta. You integrate and you get a function of zeta, right? That means it's an operator from something to something, functions to functions. You integrate, you get a function of zeta. This thing is equal to the integral around the small boundary of this thing, of h of z, Cauchy kernel, zeta, around the small boundary. Right. The integral around the two boundaries is 0. The orientations are different, so you get the right sign. It says we put a square around this thing like that, and we can use the Poisson's method by just dividing all this stuff and making the estimate, and we get the integral is equal to 0. It's exactly the same as the Gaussian. You just do the calculation now. So this equals the limit as epsilon goes to 0. Epsilon is, as far as I'm concerned, is the radius here, or something like this. It doesn't matter. You do the calculation of that. And this is exactly the point with the Cauchy kernel. You do the computation, what this is around that small square, take the limit. It's a trivial fact. This limit, let me just write it down. The reason I scaled it this way is that it is that. You get the function back, yes.
Age of?
Huh?
Isn't it age of zeta?
Boy, it's so hard for me to understand.
Isn't it age of zeta? Because f, who's f?
Oh, it's h. I'm sorry, h is the holomorphic thing here. I'm terribly sorry. Okay? Okay? Okay. So, we have h of zeta equals, I'll write it out long for you once, and do around the rectangle of f of z Cauchy kernel, c d z. Let's write it down, 1 over 2 pi I, integral around the boundary of r, f of z over z minus zeta d z. There's Maria again looking at me with a nasty look. Thank you very much. Oh, I've got so many F's and Z. H for holomorphic. I'm sorry. Okay? That says that holomorphic functions can be represented by the Cauchy kernel as boundary integrals. Now watch. Now watch. 1 over 2 pi I. Integral around the boundary of r, h of z over z, I factor out a z, 1 over 1 minus zeta over z, dz. Well, zeta, z is very far away from zeta. Yeah. Z is very far away from zeta. So in fact, if I take a circle here, if zeta is inside the circle and z is outside the circle, a circle with center at zeta, if z is outside the circle, then this quotient zeta over z is less than 1. So this is equal to 1 over 2 pi I. Integral around the boundary of r, h of z over z, times the sum, convergent uniformly on that disk, of zeta over z to the n dz. Okay. Well, I can see that I made also a technical mistake here, maybe. Let me think. So I want a power series in, this is equal to FH, this is equal to H of zeta, and this is a power series in zeta, and, right? And now do I have the right estimates here? So Z is running around the boundary here. And this did, oh, okay, I see what the point is. Well, what do I need to make? I want a conversion power series. So zeta is inside some circle and Z is outside some circle. Okay. So, okay, I'm going to put a 0 here. Okay, now it's correct. Right? If I put 0 in that circle, and zeta is inside the circle, and Z is outside the circle, then Z over Z is less than 1. And all I did here was make some translation which changes nothing. Okay? So I put a circle there. Okay, then it's okay. And the end result is that H of zeta is equal to a sum. This is a uniform conversion just with the geometric series of A n zeta to the n. Right? Yeah. And the coefficient, of course, is A n is this integral 1 over 2 pi. It's the Cauchy kernel integral of H of Z over Z to the n plus 1 dz. Integral. Okay. From the boundary of RX. Yeah. Okay. This is called the Cauchy integral formula, but not only that, it shows the regularity. It's a power series. It is uniformly convergent. What mathematical theorem we used here, this is the geometric series here conversion. We used the uniform convergence of the geometric series. You can exchange it with the integral. Yeah.
So how come if we're now using the integral over the R epsilon?
No. Oh. Yes. It's.
Are we taking some sort of limit there?
I see your point.
Shouldn't it be just R? Yeah, point of R.
Yeah, wait a minute, yeah. So first of all, you agree with the picture. I put 0 in someplace in there that doesn't hurt anything. I have a disk around that, and we can assume I'm sorry, I've gone over and I apologize for this is R. Right? Right? Because the outer integral equals the around R is equal to the it is what Nico said. It's equal to the integral in here, but then I took the limit to get that. Okay, so the outer integral is equal the outer integral equals this. Everything is integral over R. Well, I wrote R here. Yeah, I wrote R here. But what you're smelling is what I need for this thing, the power series development, is some uniform convergence. So I can exchange, so I use a geometric series here to go back and forth with the uniform convergence, right? So I need to have this disk, this disk be small. So the disk has to, we need the distance, so zeta, so if I put 0 here, that means Z is always outside the disk and zeta is always inside the disk. So that means zeta over Z is in absolute value smaller than 1, right? But I never use the integral over the circle or anything. And I really never use the integral over R epsilon. I had to take the limit, right? Okay. And the limit is exactly the same as this Gaussian discussion. You just do the calculation. Okay. So this thing here is the quotient of the formula. Where does it go? Right. Quotient. Okay, thanks for your patience. See you tomorrow.